I think my screen is visible to all. Thank you. So we will open LT Spice and we will create new file by using shortcut Control plus N. So I will tell you the step for designing. So the first we will start with specs. So what is the specs for amplifier? So specification like will be design a common source amplifier with gain of 10 or bandwidth of some hertz and the power dissipation. So I will start with gain with 10 and the maximum power dissipation should be 20 microwatt and VDD should be 1.8 for 180 nanometer technology. So these are my specs for today's amplifier. So we will start with these specs. So first of all, कल से टाइम से ज्वाइन किया करें, इसमें बार बार दिक्कत होती है, इसमें बार बार एडमिट करने में. So first of all we will calculate ID. So how we calculate ID? Anyone can please tell?
Power dissipation is equal
Power equals to VI.
So we know that the power dissipation is equal to VDD into ID. So the ID is drain current. So we can find the ID equal to how much? Please calculate.
11.11 microampere.
11.11 microampere. So I will take ID equal to 10 micro for designing. Okay. If I take ID equal to 10 microampere, then the power dissipation will be 18 microwatt, which is less than the specs. So in case we have to increase the gain by increasing ID, then that time the power dissipation rule will not be violated. So I will take ID equal to 10 microamps and then I will find out the value of W by sweeping method. So width will be from sweeping and I will take length as 360 nanometer. So the minimum length for 180 nanometer technology node is 180 nanometer. So we will take 2L, that is 360 nanometer. And in specs the technology node we can define technology node equal to 180 nanometer. And then we can also find out the different values like R and DC voltage for the MOSFET. So first of all we will create the schematic to find out the value of W, that is width. So I will take NMOS 4 transistor and place it here. And this is the schematic. I will draw the schematic to find out the width of the transistor corresponding to that current, that is id equal to 10 microamps. So I will take two voltage source. By pressing V in your keyboard, the voltage source will attach in your cursor. So I will take two voltage source and I will connect them like this. I think you all know how to take wire. Is anyone who have confusion how to take wire? I am using shortcut here. So you can take wire from this icon, and here it is written that by pressing simple W, wire will be attached in your cursor. And to skip, uh, if you have to remove the wire, and I will take ground by simple pressing G, and I will place like this. We know that the VDD of 180 nanometer technology node is 1.8 volt. So our DC voltage at output will be around half VDD. So the V out DC, we will keep V out DC as 0.9 volt. Okay. Generally we said V out is equal to half of VDD. So we will set 0.9, and what we will apply here. So yeah, this is called biasing of the MOSFET or amplifier. So there is two signal in amplifier. The first one is biasing and the second one is signal, that is small signal. So we need to find out the DC biasing for this source. That is we need to fix the VGS of this transistor to operate in saturation region. So how to find the V in for this amplifier? So there is one formula, gain is equal to GM into RD. We all know this formula, okay? And we also know that GM is equal to 2ID upon VOB, that is overdrive voltage. And first we can find the value of RD. So we can find RD by simple KVL equation. First I will create another schematic for just I am creating right now the complete CS amplifier. So to find the value of R, we will apply KVL equation at this node. So we will start with VDD minus ID RD. We can rename this ID RD equal to V out. So we will write this equation here. So VDD minus ID into RD equal to V out. Any confusion here in this equation? VDD minus ID RD equal to V out. This equation will derive from here. So we will start with VDD minus ID RD, that is the current flow voltage drop across this resistor, equal to V out. So we assume that the V out, the DC V out should be 0.9. So we can find the RD from here. We know the VDD equal to 0.8 and V out is equal to 0.9, and we also know the ID equal to 10 micro. So there is a one variable here, and we can found that RD equal to. So anyone please put the value in the equation and find out the value of RD. Anyone can please calculate.
90 kilo.
90 kilo ohm. Others?
90 kilo ohm.
Okay, I am writing 90 kilo ohm. Okay, if anyone will get different answer, then they can tell me. So 90 kilo ohm is right answer. Okay, so I got the value of RD, then I will apply values in this equation. So the final equation will be AB is equal to 2 ID upon VOB into RD. So we have the value of RD, ID and AB. AB is equal to 10. So we can find out the value of VOB. So please calculate the value of VOB by putting all the values in this equation that is highlighted here. Everyone will calculate and tell me the value of VOB.
One point eight
181.8
millivolt.
millivolts.
Say again. 0.18 volt
जी
1.8
भाई.
millivolt.
or 180 millivolt. This is okay. And we know that the VDS should be greater than equal to VGS minus VTH. So this is the equation for saturation region of a MOSFET. Okay. And we will assume VDS as VOB. So VOB equal to VGS minus VTH. And for this 180 nanometer TSMC technology, we will assume the VTS is equal to 0.45 volt, and we have VOB, so we can calculate the VGS from here. So the VGS will be VOB plus VTH. So put the value in this equation and find out the value of VGS. So VGS comes out to be
0.63.
0.63 volt. Okay, so we got the value of VGS, and here we will apply VGS is equal to, I will rename this as VGS. So VGS is equal to 0.63 volt, and I will set the length as 360 nanometer, and I will make W as variable. So I will name this as WN. So to print this value, press Control of your keyboard and then right click and then here OK, and that value will be displayed in your screen. So I have applied VGS is equal to 0.63 and this you can name as V out or VDS simply 0.9, and then I will include that TSMC file. So I will write command like dot include TSMC, the name of that file tsmc.txt, and I will place it here, and I will save this schematic in the same folder where my TSMC 180 file is located. So I will save, so I am using the same folder analog design, so I will rename this as CS Amplifier and most sweep. This is not amplifier, this is the schematic for finding width of the transistor. So now I will define what is WN. So I have to define the what is WN. So I will define W1 as dot param 1u. This is the initialization of the variables. So I have used another variables WN. So I have to initialize the value of this variable. So I will initialize this variable as 1 micro, and then I will sweep this W to find out the actual W with corresponding to 10 microamps. So I will write another commands as dot step param, name of the variable starting. I will start with 1 micro to 10 micro at the step of 0.5 micro. So you can right click here and see what is these are the values. So the name of the parameter is WN, and this is the sweeping like linear, and start value will be 1 micro, stop value will be 10 micro, and the increment will be 0.5. So I will save this schematic and I will run the schematic. So stop time. Is I am missing anything? Dot op. So it is taking some times. So we will wait some. There may be some. So we can see that the graph has been plotted and starting from 1 micro to 1.5. So I have given 10 micro. Okay. So wait for some times. It seems it is hanging. So यहाँ पे मेरा लैपटॉप पे कुछ इशू है, कुछ हैंग हो रहा है, तो थोड़ा सा वेट कर लेते हैं हम लोग. थिंक मेरा लैपटॉप हैंग कर रहा है फिलहाल। थोड़ा वेट कर लीजिए, मेरा लैपटॉप हैंग कर रहा है फिलहाल। So you can see that the starting from 1 micro and the stop will be 10 micro. Okay, and we will plot id. So we can see that this is a graph between id and w. So our id is 10 micro. So
And
I will simply left click here, then the cursor will be attached. So by moving right and left, we can find that the id will cross id will be our 10 micro. So we can see that the y-axis, that is 10.09. So we can take these values. Okay, so corresponding to this, the width of the MOSFET is 1.32. We can take value of 1.32 micro. So we got the value of w. So the value of w will be 1.32 micrometer. Okay, so for designing common source amplifier with resistive load, we need three parameters. The first parameter is rd, and the w and l. So we have assumed l, so we also find out w. And the third is the dc voltage in the gate, and we have also find out that. So we calculate all the values, and we will simulate by putting all the value in this schematic. So I will take two voltage source, one for vdd and one for vgs. So you can see here I have connected this voltage source and this node using wire. So there is an efficient method to connect this. So I can use the level net. So if I name this level, this node and this node with same name, so it will be like connected through wire. So I will use this level net and I will make it like VDS. So if I put the same name here and here, then it will be like it is connected like this. Okay, so I will use level net for our schematic to be clean. So I will make our schematic like this, and we'll copy this name and paste. So this is our VDD, and the VDD should be 1.8, and place ground here. And I have to connect these sources to gate. So I will not use the wire, I will use level net. So I will put the same name like V in. So if I put V in here and here, then it will seem like that is connected through wire. So I will put the value 0.63 as we have calculated earlier, and I will put the length as 360 nanometer, and we got the value of WL 1.32 micrometer, and I will print these values, and I will put the RD as 90 kilo ohm. So as we know that the value the inbuilt values is the different device or transistor or capacitor. So the in resistor the ohm is the default units. So to put the value of 90 kilo ohm, we need to write 90 k for 10 to the power minus 3. And similarly for length we need not mention meter. So by default it will take meter. Okay. And then for voltage by default the unit is volt. So 0.36 means 0.36 volt. So our schematic is done, and we will include that tsmc file. So I will copy this tsmc file and will paste here. First of all we will calculate the gain. So the command for gain is dot tf is a reserve keyword, and then v, and in the small bracket the node voltage to be written. So the node voltage is, I have renamed this node as V out. So V out is a node name and slash, and here we will apply voltage input voltage source name. So the voltage source of this, the name of the voltage source of input is V2. So we can write V2. The syntax I am repeating, the syntax of transfer function is dot tf v, and we will write the name of node voltage. So if anyone has written different name of this node, so according we can change these values. And this is for the source name of this input voltage. So the source name of the input voltage is v2. If I write v in, then I have to change here. We will I will rename as vin. So this vin is the node name, this is not the source name. This is for connecting from this point to this point, and I have renamed this voltage source as vin. So I will write the command for transfer function this, and then we will hit the run button. And as you can see that we have designed for 10, and the transfer function comes out to be 11.3, which is greater than our desired value. So this is we want we want the gain as maximum as possible. So the for specs the gain is given as minimum, so minimum 10. So the gain not fall less than 10, and we assume that the power dissipation should be maximum. So the gain is minimum and power dissipation is maximum. So this is the specs for any amplifier. So we have successfully designed the common source amplifier with gain of 11.3. So now we will simulate this circuit uh, in a different way, like transient AC simulations. So I will run the transient simulation from for this amplifier. So I will apply the sine voltage at the input, and I will see the output voltage from this node. So to apply the sine voltage, go to advanced setting, sine, and the DC offset should be 0.63. Sorry, and the amplitude I am keeping as 1 millivolt, and frequency as 1 kilohertz, and leave that the rest, then press OK. So I have applied the sinusoidal signal at the input, and I will see the output voltage from here. So the command for transient is dot trans as a syntax, as an reserve keywords, and the stop values. So I have applied the frequency sine wave with frequency of 1 kilohertz. So can anyone tell me what will be the time period for this signal?
1 milli
1 millisecond.
second.
Okay. So the time period is 1 upon f. So f is equal to 1k, and if you calculate 1 upon 1k, then you will find that the time period is 1 milli. So I will plot 2 cycle. So to plot 2 cycle, I will have to apply 2 millisecond. Okay. So if I write syntax like this, so this is the syntax for transient analysis, and I will hit the run button and run dot transient. wait for some time. तो आज थोड़ा सा मेरा लैपटॉप हैंग कर रहा है, आपको इतना टाइम नहीं लगेगा वैसे. So first of all we will save this schematic in the same folder. So I haven't saved this folder till now, so I will save this schematic in the same folder, CS Amplifier. Now I will run this. So so this is looking like different, so we can change the setting here. We can use, so this is the input waveform. So you can see that this is the peak to peak signal will be. So this is the DC level. The DC level is, we have applied the DC level of 0.63. So the DC level of this signal will be 0.63 volt, and then we have applied the small signal as 1 millivolt. So peak to peak will be 2 millivolt. So if you can see that, and take another cursor and place it here. So you can see that the peak to peak voltage will be around 2 millivolt. Okay. So this is the input for this amplifier, and then we will plot the output. So we can take another plot, and we can plot here output, that is the V out. So this is the output curve, output signal of this amplifier. So we can see, we know that the CS amplifier is inverting amplifier. Okay, the gain of the expression for gain of CS amplifier is minus GM over RD. So the output will be inverted version of the inputs along with multiplication factor again. So we can find out the peak to peak voltage of the output. So to find the peak to peak of, simply left click here and take another cursor by left clicking here, and then the first, we will put one cursor at top and the next cursor will be bottom. So here we will see the difference, and peak to peak voltage of this output is 22, and the input was 2 millivolt. So if we divide the peak to peak of output upon peak to peak of input, then we will get around 11. Okay, so we can verify the gain from here also. First we will measure the peak to peak voltage of input by placing one cursor at top and one cursor at bottom. So the peak to peak of input voltage is around, it will be 2 millivolt, close to 2 millivolt. Okay, and peak to peak of output, place one cursor at top and place another cursor at bottom, and divide the quantity. So it will be around 11. So we calculate the gain of this amplifier in two ways. The first one is by simply applying dot transfer function syntax, and then we have also calculated through the waveform. And the another task is to to measure the node voltage. Okay. So as if you place the cursor here, you can see that in the left bottom the click to plot Vout, the DC operating point of Vout is 893.97 millivolt. So we assume that the output voltage should be zero point 0.9. So from here we can see that it is around our desired values. Okay. And to find the current across this MOSFET, uh, place your cursor here, and you can see that in the bottom of the screen the DC operating point ID across M1 is 10.06 microamps. So we have taken our ID as 10 micro. Okay, so the actual value is closing to our design value, so everything looks like fine, and we have designed our common source amplifier. And there is one more analysis called AC analysis. So for AC analysis we need to apply capacitor at the output nodes. So I will stress these values here, and I will apply capacitor by simply pressing C, and then I will connect the ground, and now I'm putting the value randomly like 1 pico. Okay, and then I will write the command for dot AC. So dot AC DAC, number of points 10, starting frequency 10, stop frequency like 100 mega. So put like here, and if you right click this, you can see that the typing the analysis is AC analysis, and the number of yeah, you can select any of this, but I will select this as decade for some reason, and number of points per decades. So I will keep as 10. You can keep 1 or 10 or 100. So I will start with start frequency as 10. So if we write 0, it will not accept. We have to at least apply 1 hertz. So I will start at 10 10 hertz, and stop will be 100 megahertz. Okay, and then I will run this simulation. I will have to close the other and before clicking on this button, we need to apply the AC signal in the input. So right click here and give the AC amplitude. So if you give AC 1, then then dot AC command will run. So now simulate and delete this command. So we can see that the starting frequency of this curve is 10 hertz, and the stop frequency will be 100 megahertz. Okay, here we will plot, first we will plot V out. So the voltage at V out. So this is the V out curve, and we can use an we can press A, and then this window will be open, and we will select as V out, and we will enter slash and then V in. So this is the expression for gain. So I will remove this V out. So this is the gain versus frequency curve of this amplifier. So from this amplifier we can also see the gain of this amplifier. So if we right click here and click it on linear and then OK, so we can see the gain from here also. This is the gain in terms of voltage by voltage. So we can see that the gain is around 11.3. So we can find you can find out the gain in different curve also. You can simply find out gain in transfer function. You can also find out gain in transient analysis, and you can also find out gain in AC simulation. Okay, and from this curve we can find out the maximum gain and 3 dB bandwidth and UGB unity gain bandwidth. So I will select this as decibel. So the maximum frequency gain is 21.06 dB. So to find out the bandwidth, how we can calculate bandwidth from this curve? Any guess, anyone?
-3 dB.
Hmm. To find out the bandwidth, we simply maximum frequency is 11.06, and if we if we subtract 3 dB, then we will get 18.06. Okay, so place the cursor at 18.06. So 18.06. So the bandwidth of this amplifier is 1.95 megahertz. Okay, so we can find out bandwidth from here, and we can also find out the UGB, unity bandwidth. So to find out the unity bandwidth product, we will place this cursor to 0 dB. So you can see that this is almost 0 dB. Okay, so 13.8 milli dB means around 0 dB. So the UGB of this amplifier is 22.02 megahertz. So I have designed the common source amplifier, and I have also simulated through different simulation method or simulation analysis, and that's all from my side. If you have any question, you can ask.